Hi, my name is Kyle Liu, and this is my presentation about hydrogen production from non-potable water using low-cost nickel electrodes. So about the fundamentals of water electrolysis, this is known as the process of using electricity to decompose water into hydrogen and oxygen via two electrodes called the cathode and the anode. Cathode being the site of reduction where hydrogen gas is produced, and the anode of where oxidation occurs where oxygen gas is produced. So why am I going to be using nickel electrodes and why does structure matter? Well, nickel has high catalytic activity during electrolysis, is very earth abundant, and has amazing electrical conductivity. Why does electrode structure matter? Well, it matters because of the fact that greater surface area provides more available reaction sites with porous structures improving hydrogen bubble release, which allow for faster reactions, as seen to the right side, where every single hair on that electrode could be a possible reaction site in comparison to just a flat nickel strip. So during this study, I'll be using my control nickel strip electrode, my experimental low-cost nickel plated steel wool, and I'll be comparing the effects of these on electrode architecture through hydrogen production. So about non-potable water as an alternative feedstock, usually these systems require a continuous supply of purified fresh water, resulting in this to have a very heavy impact on our environment, resulting in it not to be very green source of energy, as only about 3% of Earth's water is classified as fresh water. So my challenge is to evaluate the electrolysis performance in non-potable water through three things: gray water, rainwater, and tap water. Gray water is the byproduct of washing, rainwater being naturally occurring within our atmosphere, and tap water being the recycled municipal system. For my purpose, the purpose of this is to see the feasibility of low-cost nickel-based electrodes for hydrogen production using alternative water sources. I'll be comparing hydrogen production between flat nickel strips and nickel-plated ones. I will evaluate the effect of tap water, rainwater, and gray water on electrolysis performance. For my pathway, I have 5 steps. 1 being electrofabrication, 2 being water preparation, 3 being electrolysis testing, 4 being hydrogen collection, and 5 being data analysis. For my methodology of porous electrofabrication, I used two things. One being the steel wool from a hardware store, and two being a nickel anode. I would then plunge them into solution, and this nickel anode would be the sacrificial one, meaning that it transfers its own nickel ions onto the steel wool, allowing it to plate. So this was a 3-day process, which then resulted in a nickel-coated porous electrode, around a 23-gram mass increase, an increased active surface area, and a more rigid conductive structure. For my experimental setup, as we can see to the left side, this was all 10 of the materials that I had used during the entire setup. And over to the right side will be my actual setup of a cathode and an anode. Usually these two would be plunged into a vat of my own feedstock, which is the liquid plus my sodium bicarbonate electrolyte. These two will be plunged inside with cathode being contained by a plastic structure. This plastic container would then be filled to the brim with water, allowing it to not have a single air bubble. Using a method called gas displacement, I was then able to calculate the amount of H2 that I had just collected. So as H2 comes in, as it's produced by the cathode, it would then push out the water, displacing it outside back into the container. Using the formula found below, I was then able to find the H2 amount, which was the total amount or the total container in milliliters, subtracting off the milliliters left after reaction. Finding this difference then allowed me to find the H2 that I had just collected for that separate trial. For my feed water properties, I collected it from the tap water, rainwater, and gray water. pH, nothing remarkable, but TDS and salinity did have something remarkable. Gray water featuring around 568 milligrams per liter of TDS, which quantifies the dissolved solids and ionic content within each. And gray water, once again, having the greatest conductivity and the number of ions, salt ions within this liquid, meaning that it was technically the most conductive out of these three. For my results in the hydrogen production performance, we see that rainwater had a major increase in hydrogen production compared to tap water or gray water, with the rainwater porous nickel steel wool increasing the hydrogen yield by around 20 milliliters in comparison to flat nickel strip. For tap water, there was only maybe a 1 milliliter increase with only a marginal increase in tap water in comparison to the flat nickel strips and the porous nickel steel wool. For gray water, we actually see that the porous nickel steel wool actually kind of suffers a little bit in comparison to the flat nickel strip. And this can most likely be attributed to the various chemical and physical properties of the wash water and how bubbles and how its characteristics form within each system, resulting in it not to be very consistent by case basis. For my electrical data that I collected throughout the entire experiment, I collected the currents and the runtime. Using these two values, I was then able to calculate the charge pass. Using this value, I was then able to calculate the theoretical maximum amount of H2 volume that I could produce with my reactor if it had been running at 100% accuracy. For the right side is my experimental H2 volume, which I actually collected. And on the right of that is going to be my Faradic efficiency, which measures the electrical to hydrogen conversion efficiency. So as we know, tap water and rainwater did the best with porous nickel. If we compare the two, the flat nickel to the porous nickel during the tap water trial, porous nickel had actually a 7% efficiency increase if we compare the two. For rainwater, comparing the flat to porous, we actually see a 5% efficiency increase too within those two, with only the gray water marginally losing by a small amount. For cost efficiency, I calculated the unit fabrication cost of each one, the porous nickel and the flat one. As we can see out of the six, the lowest yield per dollar was actually the flat nickel strip and the tap water source, with only about 3.1 milliliters of hydrogen being produced per dollar. For rainwater and the porous nickel, this one actually produced the most out of the six, with 114.2 milliliters hydrogen per dollar spent, showcasing that porous nickel during this rainwater trial actually shows the highest return on investment and possibilities for the future to come. These are my calculation proofs that I had used during this entire data collecting experience. My limitations of bench scale testing, limited trial conditions, electrodurability, and gray water reliability, specifically how bubbles in chemistry related to what contaminants are within the water, results in variable outcomes depending on situation on a case-by-case basis, once again. For my conclusions, I found that the porous nickel-plated electrode produced greater hydrogen output while increasing electrical to hydrogen conversion efficiency by 7% in tap water and 5% in rainwater feedstocks. The porous nickel-plated electrode achieved up to an 8.7 times greater hydrogen yield per dollar compared to that with the flat nickel strip. For the H2, there was also H2 was successfully generated from all three hot water sources, demonstrating that there is feasibility of freshwater independent electrolysis for the future. For future directions, I hope for real-world implementation of household and municipal wastewater electrolysis systems. I hope for hydrogen energy applications of hydrogen fuel cells, backup power systems, and industrial hydrogen production. I hope for advanced electrode development and catalysts, coatings, and reduction of costs. And I hope that hydrogen energy becomes worldwide and available and affordable for all those to come. These are my references and my acknowledgments. Thank you very much.